Welcome to this explainer. Today, we're doing a real deep dive into the incredibly intricate science of electrolysis. We're going to take you on a truly fascinating journey, starting way down at the microscopic level with the fundamental manipulation of electrostatic forces and single electron transfers, all the way up to the massive, roaring industrial vats we use for global metal extraction. It is a highly complex, phenomenally powerful scientific process that quite literally shapes the modern physical world we live in.
Since we're tackling some heavy, complex concepts today, here is our roadmap. 1. Core principles. 2. Splitting molten salts. 3. Aqueous rules. 4. Aluminum extraction. And finally, 5. Electroplating.
All right, Section 1. Core Principles of Electrolysis. Think of electrolysis as the ultimate chemical tool for splitting compounds apart. But, it requires a very specific, highly controlled environment. It's important to remember that this only works for ionic compounds. Covalent compounds simply do not conduct electricity, so they just won't work here. To force this chemical breakdown to happen, we have to pump a continuous direct electric current through the setup. It has to be direct current, not alternating, so that our poles maintain their strictly designated positive and negative charges at all times. We pass this current through completely unreactive rods, usually made of something like platinum or graphite, which we call our electrodes.
Now here's a fundamental rule you absolutely have to keep in mind. Ionic compounds, they simply cannot conduct electricity when they're solid. The individual ions are locked way too tightly into this rigid electrostatic crystalline lattice. The bonds are just too strong. So for electrolysis to even begin to work, we have to pump in enough thermal energy to fully overcome that lattice energy. We have to literally melt the compound down into a liquid or dissolve it completely into a solvent like water. It's only in those fluid states that those charged ions are finally freed up to move around and carry that vital electrical charge from one side of our setup to the other.
So when we look at the physical layout of the cell, you can see how this opposite attraction mechanism actually works as the engine for the whole process. The positively charged cations naturally migrate across the electrolyte over to the negative electrode, the cathode. Meanwhile, the negative anions are rushing in the exact opposite direction toward the positive electrode, the anode. It's this continuous, dual-directional flow of physical ions that literally drags the electric current right through the chemical bath.
Moving on to Section 2. Splitting molten ionic salts.
To really navigate these highly intricate electron exchanges happening at the electrodes without getting totally lost, you've got to memorize this absolute classic chemical mnemonic. OLIRG. Oxidation is loss, reduction is gain. Remember, electrochemistry is fundamentally all about the precise, calculated transfer of electrons. If you can understand exactly where those microscopic electrons are going, you've basically unlocked the entire thermodynamic puzzle.
So, practically speaking, what does this mean? Well, oxidation, that loss of electrons, always happens at the anode. As those negative anions hit the microscopic boundary layer where the positive anode meets the electrolyte, they're forcibly stripped of their extra valence electrons. They are oxidized. On the flip side, the positive cations reaching the boundary layer of the negative cathode actively scoop up those electrons to complete their outer shells. They are reduced.
Let's look at this in action with molten lead bromide. When we apply these exact rules in the lab, it's honestly a spectacular demonstration. We have to strongly heat the salt in a crucible until it hits its melting point. Then, when we pass a heavy direct current through it, we literally watch a silvery lump of pure molten lead start to pool at the negative cathode. And at the exact same time, this obnoxious brown, highly toxic vapor of bromine gas aggressively bubbles off at the positive anode. Microscopically, the lead ions are gaining 2 electrons to become stable, neutral atoms, while 2 bromide ions each lose an electron to pair up covalently as a neutral diatomic bromine gas molecule. It is chemistry in pure observable motion.
Okay, so we've got molten salts down. It's just 2 specific types of ions playing the game. But what happens to the underlying thermodynamics when we dissolve these salts in water instead of just melting them?
That brings us to Section 3. Intricate aqueous solution rules.
This is where things get genuinely intricate, because water naturally introduces its own competing hydrogen ions and hydroxide ions into the electrolyte. They immediately start a chemical tug-of-war with our compound's original ions. This all comes down to strict standard electrode potentials, a fascinating concept known as preferential discharge. At the cathode, if the dissolved metal is highly reactive, meaning it heavily prefers to exist as an ion, like sodium or potassium, it just stays safely dissolved in the water. Instead, hydrogen gas is discharged because it requires significantly less energy. At the anode, if a halide ion like chloride or bromide is present, it possesses a lower discharge potential, so it wins the race to become a halogen gas. But if there isn't a halide present, the hydroxide ions from the water take over and pure oxygen gas is produced instead.
This data table does a great job meticulously summarizing the end results of these intense chemical tug-of-wars for some common solutions. Take a really close look at the fascinating anomaly here with sodium chloride. In a highly concentrated solution, which we call brine, the sheer, overwhelming volume of chloride ions totally outnumbers the hydroxide ions, meaning chlorine gas is forcibly discharged at the anode. But if you simply dilute that exact same solution with more water, the thermodynamic preference shifts right back. The hydroxide ions win, and we get oxygen instead. Meanwhile, because copper sits way lower on the reactivity series than hydrogen, electrolyzing a copper sulfate solution yields actual pure copper metal precipitating directly at the cathode.
Let's completely scale things up in Section 4, Industrial-Scale Aluminum Extraction.
Before electrolysis can even begin on an industrial scale, we have to deal with the raw ore, bauxite. It's only about 50 to 65% alumina, so it has to go through a highly complex, multi-stage chemical purification known as the Bayer process. Because aluminum oxide is amphoteric, meaning it uniquely acts as both an acid and a base, engineers crush the ore and mix it with a hot, incredibly strong alkali, like sodium hydroxide. This cleverly reacts with the aluminum oxide to form a highly soluble sodium aluminate solution. Crucially, it leaves behind all those stubbornly basic, completely insoluble impurities like silicon, iron, and titanium oxides. Once those are meticulously filtered out, the remaining liquid is treated and heavily heated to yield a brilliant pure white powder, pure aluminum oxide.
Once we have that perfectly purified powder, we dump it into massive industrial vats. We're talking a staggering 8 meters long and a meter deep, rigged up with incredibly thick carbon electrodes. Hundreds of thousands of amperes of electrical current will pass through these giant vats. This right here is where the true roaring magic of industrial chemistry happens, transforming that refined powder into the robust, lightweight metal that builds our modern aircraft, spacecraft, and structural components.
But we hit a massive, seemingly insurmountable engineering hurdle right away. Pure aluminum oxide melts at an absolutely devastating 20-40 degrees Celsius. Maintaining that extreme level of heat on a massive scale would be economically ruinous. Plus, pure molten alumina is actually a remarkably poor electrical conductor. So, engineers brilliantly introduce a molten solvent called cryolite. This expertly forces the working temperature down to 1,000 degrees and with a calculated dash of calcium fluoride, drops it even further to a much more manageable 900 degrees. Not only does this save truly astronomical amounts of expensive thermal energy, but the resulting mixture is a vastly superior electrical conductor. It's an incredibly elegant solution to a massive industrial problem.
And here is a deeply fascinating side effect of operating at this massive scale. Think about what's chemically happening at those positive electrodes. Oxide ions are violently losing their electrons to form pure oxygen gas, right? Well, that intensely hot, highly reactive oxygen gas immediately starts attacking the solid carbon electrodes themselves, literally burning them away into carbon dioxide gas over time. Because of this relentless, unavoidable oxidation of the equipment, these giant, super expensive carbon blocks have to be routinely monitored and fully replaced. It presents a constant, highly intricate logistical nightmare for these giant smelting factories.
Finally, let's wrap up with Section 5, the practical magic of electroplating.
Let's zoom way back in to the microscopic level. By purposely making the specific object you want to plate, let's say a plain steel spoon, the negative cathode, and using a solid block of pure plating metal like silver as the positive anode, we can meticulously coat intricate surfaces atom by single atom. The silver atoms at the anode are heavily oxidized. They lose electrons and dissolve seamlessly into the electrolyte as silver ions. Those newly formed ions are then powerfully drawn across the solution to the negative steel spoon, where they gain their electrons back and perfectly plate themselves onto the surface in a uniform, microscopic layer. Fascinatingly, for every single silver atom plated onto the spoon, exactly one dissolves from the anode. This means the ionic concentration of our electrolyte remains in perfect, dynamic equilibrium throughout the entire process.
So, zooming out for a second. Whether we're looking at roaring, massive industrial extraction vats running constantly at 900 degrees, or a highly precise, microscopic metal coating happening quietly in a commercial vat,
Why exactly do we go through all this immense, highly complex electrical effort?
Ultimately, mastering this incredibly intricate, microscopic transfer of electrons is exactly how humanity manages to violently pull pure, useful elements out of otherwise unreactive, stubborn rock. It's how we galvanize weak steel with a protective layer of zinc so our towering skyscrapers and massive suspension bridges don't succumb to structural rust. It's how we delicately coat our fine jewelry in pristine silver, and how we engineer the hyper-resilient, beautifully lightweight aluminum materials that literally build our entire modern world. So the very next time you look up and see a commercial airplane soaring overhead, or you just sit down to use a beautifully heavy piece of silver cutlery, ask yourself, just how many billions upon billions of individual electrons had to be carefully, deliberately moved to make that single object possible?